Hello, we are Team SpyCat from Kansas State University. My name is Caleb Fleming. I am the team captain and a senior in computer science. This is my third year on the team with 3 years of UAV experience, and my responsibilities on the flight line will include being the main interface between the lead judge and the team, as well as overseeing all of the no-go conditions.
My name is Stephen Blitz. I am a senior in information systems. I've been on the team for 5 years, and my experience with UAV is fairly extensive. My role on the team is as the image analysis team lead, and primarily I've been working on the update for the software, and my flight line participation shall be ensuring that the software works within expected parameters.
Hello, my name is Blake Smithers. I am a senior in computer engineering. I've been on the team for 4 years, and I have about 4 years of experience with UAVs. I was the president last year, and this year I am the safety officer. And on the flight line, I will be working on communication with all team members and ensuring that the flight is safe at all times.
My name is Joseph Hoskinson. I'm a freshman in mechanical engineering. This is my first year on the team. I've had around 3 years of experience with UAVs. My role on the team is dealing with communications. My responsibility is making sure we're communicating effectively with the aircraft, and my flight line participation is antenna tracking.
My name is Alex Kim. I'm a junior in mechanical engineering. This is my second year with the team, and my responsibility in the team is allocating and keeping track of funds as a treasurer. I gained my experience with UAVs since I joined the team. My flight line participation is making sure the airframe is ready for the flight.
My name is Ben Hauer. I'm a senior in mechanical engineering, and this is my third year on the team, so I've had about 3 years of experience with UAVs. I'm the current head of the airframe subteam, so I coordinate the construction and maintenance of the physical components of the aircraft, and on the flight line, I will be making sure the UAV is ready for flight.
My name is Tyler Hinnon. I am a junior in electrical engineering at K-State. I've been on the team for 3 years. I am currently the vice president. I am responsible for the majority of the electrical system on the aircraft, and I'm also one of the safety pilots. My experience with UAVs is that I grew up flying RC planes, and I've kept that hobby going throughout my life, and I am still very active now, mostly with multi-rotors and FPV. But I also still work with the UAV team. Our airframe is an octocopter design that utilizes carbon tubes as the arms of the aircraft. At the end of each arm, there is a DJI E800 series motor and ESC attached, which are powered by a 22,000 milliamp hour 6-cell Tattu LiPo battery. For remote control, we have a FrSky receiver sending signals to a Pixhawk flight controller, which communicates over a 900 megahertz radio as telemetry to our ground station. We have a Raspberry Pi 3 and a Zotac Z-Box doing onboard image analysis and autopilot control. Those two are fed together through a commercially available network switch and to a 2.4 gigahertz PicoStation Bullet radio. For camera, we are using a Sony QX1 on a 2-axis gimbal using a custom-designed STM32 controlled gimbal controller.
For development of our UAS, we had to complete several tests to ensure the integrity of each system. Types include in-lab bench tests, range tests, and full flight tests for each individual component. In-lab tests are conducted to establish reliable performance under stable conditions. Range tests allow us to test under less ideal or constrained conditions, but in a controlled environment. Flight tests demonstrate the integration of a new component into existing complete infrastructure. The systems tested with these methods include autonomous flights, waypoint accuracy, object detection and classification, air delivery, and full mission tests. Over the course of the semester, we completed 20 autonomous flights. On average, each flight had less than a minute of manual flight, depending on whether or not we were completing autonomous takeoff. We began tuning our aircraft with bench tests to tune the PID control loops until the aircraft was able to precisely respond to outside interference. To confirm that the aircraft was tuned properly, we completed a series of manual flights, moved on to tuning the autonomous functionality of the autopilot. We began testing with a set of very conservative settings that we felt were far below the system's capabilities. We then slowly increased the limits on aspects such as the maximum velocity and maximum ascent speed until we felt the system had reached an unstable state. We then toned back the limits to well within our newly determined boundaries to serve as our standard configuration.
We know from previous test flights that our autopilot waypoint accuracy is consistent. Tolerances set within autopilot only allow the aircraft to continue to the next waypoint if it's within 5 feet of designated coordinates.
We've been working with the Sony camera since 2015, performing 15 flights with autonomous camera triggering. Our resolution is 5,456 by 3,064, and in order to obtain the best image quality, we take a picture every 5 seconds. For autonomous classification and detection, we developed an algorithm in MATLAB which, unfortunately, had issues with false positives and unreliability with optical character recognition. As a result, we have elected to have human interaction provide the final go, no-go confirmation. We used 3 targets for testing, and, after 7 test flights, we have been able to achieve a localization error within approximately 50 feet.
For the testing of air delivery task, we dedicated 4 flights with a total of 12 drops just for the delivery mechanism and to see if the water bottle survives the drop. In order for the water bottles to survive the drop, we used duct tapes for the rigidity and a ribbon to increase the drag of the bottle. As for the drop, out of 9 drops at 100 feet, 8 water bottles survived, but all 3 dropped at 200 feet did not survive, landing on a concrete surface.
The team has conducted several full mission tests, during which we attempt to replicate the conditions of actual competition flight as closely as possible. This includes limiting team member communication to radio only, performing all mission and competition tasks in the allowed competition time frame, and performing all of our standard go-no-go pre-flight checks. Our tests begin with autonomous flight, flying waypoints programmed by our autopilot team at their ground station. We generally then proceed to air delivery, followed by object detection, classification, and localization. Such testing has not yet revealed major flaws in our system, as most of these are caught during the individual component testing stages. In terms of full mission projected scores, for timeline we expect to receive about 38.8% of the possible points. During testing, our pre-flight setup, calibration, and final checks come in well under the allowed 20 minutes, and full mission flights generally take less than half an hour. We project around 97.5% of the available points for autonomous flight. This is due largely to the accuracy constraints of our autopilot software mentioned earlier in the presentation. Since the team has elected to not perform the obstacle avoidance task, there will be no points awarded in this category. Object detection, classification, and localization has proved particularly difficult, and so we expect to receive about 50% of the points in this category. Air delivery, on the other hand, is generally very accurate given the ability of a multi-rotor to hover in one place. So the only real error in our system generally comes from the bottle bouncing when it hits the ground. So for air delivery, we project a score of about 93% of the possible points. Everyone on the team knows their roles well, and we operate smoothly as one unit, so we expect to do well in operational excellence, at least 75% of the available points. Taking all of these individual categories and their weights as part of the overall mission demonstration, we would expect at this point to receive about 59.7% of the overall points for mission demonstration at competition.
As you can see, our team has thoroughly tested every aspect of our system to ensure that it reliably performs the task that it is set out to accomplish. Our team is confident that our system as a whole will perform reliably and safely, completing every task that it sets out to accomplish this year.